Shit's not personal. Lately it's been feeling kinda mutual. We're crazy if we think it's more than sexual. Cause I know you can feel this distance. I won't offer no resistance, no.
Here we go.
Oh, don't look no deeper.
And advertisement for my channel. Nice.
Can't get no clearer.
But I'm not playing Lego Marvel superheroes.
You only hit up my phone when you hate being alone.
There we go.
No, there ain't no future. Ain't no future. Don't got love for you like I used to anymore. No, there ain't no future. Ain't no future. I don't fuck with you like I used to anymore. No future. No, there ain't no future. Ain't no future. Don't got love for you like I used to anymore. Anymore.
background from the project view into the hierarchy. This will create a new game object called background. This new game object is created with a sprite renderer component attached. Game objects are the entities which scenes are made out of in Unity. Each piece of a game scene, whether it's the player, a wall in the level, or a coin, can be its own game object. All game objects are created with a transform component attached to them. The transform component is used to store and manipulate the position, rotation, and scale of the object. To add additional functionality to a game object, we can add additional components. Adding a component allows a game object to do something. For example, adding an audio source component to a game object allows it to play sound. The sprite renderer component allows a game object to display a 2D image shown in its sprite field. Dragging a sprite into the scene or hierarchy is a shortcut provided by Unity. Since we can't have a sprite in the scene that's not attached to a game object, Unity creates a game object with the appropriate sprite renderer attached and automatically references the dragged sprite asset to be displayed. Because we drag the sprite into the hierarchy window, it should appear at origin or the position 000 in our world. To make sure the sprite is at origin, reset the transform component using the context-sensitive gear menu in the upper right of the transform component. This will reset the position of the game object to the coordinates 000 in our scene if it's not already there. The origin point of the world is where all of the coordinates in the scene are calculated from. Currently, we can only see part of the background in the scene view. With the game object still selected, move the cursor over the scene view and type the F key. This allows us to see the entire game object in the scene view. You can also choose Frame Selected from the Edit menu. Looking at our current scene, we can see grid lines which provide a reference for spacing in the scene. For the purposes of this project, we'll turn these off. Select the Gizmos menu in the scene view and deselect Show Grid. Now, let's create our player object. In this assignment, our player will be represented by our UFO sprite. Drag the UFO sprite into the hierarchy. A game object called UFO will be created with an attached sprite renderer component to display the sprite we dragged in. Let's rename our newly created game object from UFO to player. With the UFO highlighted, navigate to the inspector and click in the text field at the top. With the text highlighted, type player. Now we have two sprites in our game. Because sprites are not 3D objects, we need to manually determine which sprites will be rendered on top or in front of one another. The way we do this is by assigning each of our sprites to a sorting layer. If we click on the sorting layer drop-down in our sprite renderer component, we can see that there are 4 sorting layers already defined in our project. These are default, background, pickups, and player. These sorting layers are part of the project settings. They were imported when we chose to import our asset package as a complete project in episode 1. To add your own sorting layers, select Add Sorting Layer, and then click the plus button. Sorting layers can be reordered by clicking and dragging. We already have all the sorting layers we need, so we can delete this one we have just created, sorting layer asset package as a complete project in episode 1. To add your own sorting layers, select Add Sorting Layer, and then click the plus button.
Got it.
Sorting layers can be reordered by clicking and dragging. We already have all the sorting layers we need, so we can delete this one we have just created by highlighting it and clicking the minus button. The order of the layers here is important. Layers are rendered in list order from top to bottom, with the bottom layer being rendered last and therefore appearing in front of the previous layers. This means that objects in the background sorting layer will be rendered on top of objects in default, and that objects in pickups will be rendered on top of objects in background, and so on. For this project, we will use the layers and their order as defined in the project settings. Highlight the background object. In its sprite renderer component, set the sorting layer to background. Then highlight the player object and set its sorting layer to player. Next, we want to adjust the scale of our player. We can do this in a number of ways. One way is to use the scale tool. With the tool selected, simply grab the axis handle we want to change and drag the handle, rescaling the player. We can also click and drag on the title of the fields we want to change. Or we can type a number directly into the fields we want to change. We can tab between fields and hit enter or return to confirm our choice. Let's use 0.75 for the X and Y fields to scale the player to 75% of its original size. Note that because we're working in 2D space, changing the scale value for the Z or Z axis will have no effect. We can think of each sprite as a pane of glass with an image painted on it. It's flat, without depth or volume. You may have noticed that if we change either the X or Y scale values to negative numbers, the image will be reversed along the horizontal or vertical axes, respectively. So far, we've been working in the scene view, which you can think of as our work area. If we click over to the game view, we can see what our player will actually see when they're playing the game. Notice, when we switch to the game view, our view is much tighter on the player and we can't see the whole background. In the case of the game that we're trying to design, this is going to make it pretty difficult to play. So what we're going to do is we're going to adjust the view of the camera so that it can see more of the board. Let's start by highlighting the main camera. With the main camera highlighted, we'll see that it's also a game object with a header and transform, but it has a camera component attached. When we created this project, we set the project type to 2D. With a 2D project, all new cameras will use orthographic projection to render the scene. Using orthographic projection means that objects will not appear larger or smaller based on their distance from the camera. To visualize how this works, let's temporarily exit 2D mode. In the scene view, we can see our camera and our sprites. We can visualize how this works. Let's temporarily exit 2D mode. In the scene view, we can see our camera and our sprites. We can rotate the view by Alt or Option dragging in the scene. If we highlight the camera game object, we can see the camera's frustum. The frustum is the camera's viewable area. If we briefly change our camera's projection to perspective, we can see that the shape of the frustum changes, and so does our view of the scene. If we temporarily move our player game object towards the camera along the Z or Z axis, we will see that its size grows larger in the camera preview. If we switch back to orthographic projection, however, we can see that although the object is closer to the camera, it does not appear larger in the frame. Player game object. The frustum, or camera projection, means that object will not appear larger or smaller based on their distance from the camera. To visualize how this works, let's temporarily exit 2D mode. In the scene view, we can see our camera and our sprites. We can rotate the view by Alt or Option dragging in the scene. If we highlight the camera game object, we can see the camera's frustum. The frustum is the camera's viewable area. If we briefly change our camera's projection to perspective, we can see that the shape of the frustum changes, and so does our view of the scene. If we temporarily move our player game object towards the camera along the Z or Z axis, we will see that its size grows larger in the camera preview. If we switch back to orthographic projection, however, we can see that although the object is closer to the camera, it does not appear larger in the frame. Let's reset the player's position to 0, 0, 0 and make sure the camera is using orthographic projection before we return the scene view to 2D mode. Next, let's get a better view of our playfield for our camera. Click on the game view. To change how much is visible to an orthographic camera, we adjust its size field. Let's click on the size property of our camera and drag. By dragging, we can find that a value of around 16.5 works nicely. Now we can see that the player is at the center of the board and the board is sitting on a blue background. This blue background is the default for new scenes when working in 2D mode. Let's change this to something better suited to our game. We can see that the camera has a property called background. This allows us to select a background color. Click on the color swatch to open the color picker. To choose a color, we can click and drag or enter a value numerically. Let's use numeric values to set the background color. For the colors red, green, and blue, let's use the values 32, 32, 32. This will give us a nice dark gray background color. Congratulations! We now have a player game object and a background playfield. In the next lesson, we'll learn how to add a script to our player to enable them to move around the playing field using 2D physics. Now, we're going to move the player game object. First, let's think through how we want this player game object to behave. We want to have the player fly around the game area, stay on the playfield, and not fly off into space. We want to be able to collide with our collectible game objects and pick them up when we do this. This requires physics. Unity has two physics systems, one for 2D and one for 3D. These systems are comparable to each other and compatible with each other in that they can both be in the same scene, but importantly, they will not interact with each other. For this project, we'll be using 2D physics. To use 2D physics, the game object needs to have a rigid body 2D component attached. To attach a new component, we must first select the game object we want to attach the component to. In this case, we'll select our player game object. Then, we can either choose the component menu and select Physics 2D, Rigid Body 2D, which would attach this component to the game object we've selected, or use the Add Component button in the inspector, choosing Rigid Body 2D. It's important to be sure that we're adding the Physics 2D version of this component, not the Physics or 3D version, since we can choose between both the Rigid Body component for 3D physics and the Rigid Body 2D component. These components cannot work together, so be sure to choose the correct components for our game type. If we choose to, we can rearrange the order of the components on the game object using the context-sensitive gear menu in the upper right of the component. Doing this has no effect on the performance of our game. However, having a consistent order to the components on our game object may help us speed up our development by keeping or maintaining an organized project and hierarchy. Don't forget, we can collapse or expand the component view by clicking on the component's title bar. Now, we need to get the player object moving under our control. To do this, we need to get in the component's title bar. Now, we need to get the player object moving under our control. To do this, we need to get input from our player through the keyboard, and we need to apply that input to the player game object as forces to move the player object in the scene. We'll do this by using a script that we attach to the player game object. Let's create a new C# script. To create a new script, we have some choices. We can choose Assets, Create to create our new C# script, or we can use the Create menu in the project view. But what might be more efficient in this case would be to select the player game object and use the Add Component button in the inspector. What might be more efficient The fact that it's 2D physics as distinct from 3D physics, in this case, is irrelevant. We're going to put our code in fixed update. The next question is, what code are we going to want to put in fixed update? We know that we need input, but how do we find out more? There's a shortcut in MonoDevelop that searches the Unity API. On the Mac, it's Command plus single quote, and on Windows, it's Control plus single quote. Select the item we want to research, in our case input, and hold down the Command or Control key, and then press the single quote key. This search brings up every reference in our documentation related to input. Let's select Input at the top, Interface into the input system. This brings up the page on Input. This is the page on the Input class. We use this class to read the access setup in the Input Manager and to access multi-touch and accelerometer data on mobile devices. We read the text on the top of the page to understand how to use the class. In our case, to get input from the player on all platforms, including mobile devices. Under the description is a list of class variables and class functions. The class variables hold information like the number of touches in touch count or a reference to the default gyroscope with gyro. The class functions do something for us. In our case, we'll be using input.getAccess. When we find the item we want, we click on the link to bring up a page on the function or variable. Let's look at input.getAccess. This page includes the signature of the function, a description of the function, and code snippets showing us how to use it in Unity's JavaScript and C#. We will be using C#. For more information on input and the Input Manager, please see the information link below. We'll be using input.getAccess in a very similar way to the code snippet shown. Let's return to our script and write our code. Type float move horizontal equals input.getAccess horizontal float move vertical equals input.getAccess vertical. Now we can delete the input line. This grabs the input from our player through the keyboard. The float variables move horizontal and move vertical record the input from the horizontal and vertical axes, which are controlled by the keys on the keyboard. These keys are set by default in the Input Manager. Our player game object uses a rigid body 2D and interacts with the 2D physics engine. We'll use this input to add forces to the rigid body 2D and move the player game object in the scene. To know more about how to apply forces to the rigid body 2D, let's check the documentation. First, type rigid body 2D into our script. Now, select rigid body 2D and hold down the Command key on the Mac or the Control key on Windows and type single quote. Again, this brings us to a page with a search term rigid body 2D. Let's click on that. This brings up the rigid body 2D page. If we want to apply force to our player game object, we need to do something. So let's take a look at the functions available to the rigid body 2D class. We can read the descriptions until we find the one we want. In this case, let's choose Add Force. This adds force to the rigid body 2D. As a result, it will start moving. Click the link and we go to the page on Add Force. We can see the signature of the function at the top of the page. The signature tells us we need a vector 2 and an optional force mode to add force to our rigid body 2D. What is a vector 2? For more detailed information on Vector 2, please see the information link below. But in simple terms, the Vector 2 holds 2 decimal values in one container. This makes it easy for us to move around and use values for things like a force in 2D space, which requires a value for force on both the X and Y axes. All of our documentation pages are linked together. If we were to click on Vector 2, we would be taken to the documentation page for Vector 2. The next concept that we need to cover is how to get a hold of, or how to reference, different components on our game object. We're currently writing a script called Player Controller, which is attached as a script component to our player game object. From this script, we need to add force using the Rigid Body 2D component. We want to access that component from this script. There are several ways that we can do this, but in our case, we'll cover only one of the main ways.
Okay, so guys, I know it's going to go to 10. I am fading fast. I think it's just me and Homer in here. I don't know who this third viewer is.